Thank you for coming to my talk. I'm going to be explaining, actually before we start, let's look through, I'm sure a lot of people have seen this already, but this is the motivation for why this talk exists. And I will just send this to the speakers and Boston Dynamics is Atlas robot, and it does some pretty amazing things. And that's sort of what the motivation for this talk is. People see a lot of these videos. A lot of people, actually, if you see, there's like a lot of comments that just assume that it's CGI, and there's a lot of arguing about it, and there's a lot of misinformation about it. There's people that think that it uses techniques that it doesn't. And there's people that think that this is the end of the world and the robot overlords are going to chase us around with a gun. And I'm here to tell you that it's true. I'm here to tell you that it's not accurate. And I'm trying to explain exactly how do you get a robot to do such agile, such dynamic motions that they look realistic and look CGI. So, just to introduce myself, I am Raggy. I am a bachelor's and master's student in mechatronics at UQ, and I love all sorts of robots. Robots that have legs, robots that fly, robots that swim, robots that drive. I've done all sorts of robotics. A lot of it has been at CSIRO, the Australian National Science Agency. I've done some machine learning stuff throughout my career so far at Microsoft, and I'm about to join Emerson, which is a CSIRO spin-off startup. In next year when I graduate. So I've also, if you guys are electrical engineering or mechatronic or mechanical students, you might also see me around because I tutor basically half the really important mechatronics courses. Signal processing, control theory, robotics, I tutor like half of those courses. And actually so does Miguel right here. So, but you've seen these really cool robots, they can do backflips, they can dance. And as computer science majors, you know exactly how it works, right? It uses machine learning. Obviously, no, it does not. There is absolutely zero amount of machine learning in these machines. So how do you actually reach the level of Skynet? How do you get these robots to dance without letting them learn themselves? Well, this is a really beautiful idea in engineering, this beautiful field of mathematics and engineering that I love. And it's called control theory. Now, I'm going to warn everyone that there are some very mathematical looking slides. I'm not shying away from them. I think they're pretty important to see. But most of them represent really simple concepts. It just looks complicated when you put it in hieroglyphics. So what is control theory? Well, control theory, it sounds a bit stupid to say, but control theory is the field of controlling systems to do what you want them to do. Now, it sounds a bit obvious, but maybe it's better with examples. I've tried explaining it to a lot of people. In fact, I talk about control theory all the time, enough so that I have a website, and the first thing you see on the website is an actual blog where I tell you, this is the blog to come to if you see me talking about control theory. And I just try and explain it in a few different words. I'm going to go a bit deeper than that rant that I have online. And I'm going to try and explain some of the actual theory and not just what it is and why I like it. So what sort of problems does control theory deal with? All sorts. You know about robots. So yes, walking robots, walking and running and dancing robots, but also it deals with driving robots. So self-driving cars, you've got self-driving cars here. One of the biggest technologies in these self-driving cars is how they control and make decisions, and that's part of robotics too. And drones, how do they map around? How do they map their environment? That's one problem, but also how do they travel within it? How do they decide where to go? How do they avoid obstacles? How do they do backflips? Rockets and jets. The most obvious would be to point at SpaceX and point out that, how do you get a rocket to land itself, right, without it crashing? Well, yeah, that's very obvious an example, but every single rudder within an airplane, basically every single moving mechanism that needs to be controlled with any degree of precision needs control theory. Cars have all sorts of control systems in them. You've got battery control systems, you've got the actual transmission, you've got electric cars, you've got self-driving cars, you've got trucks. Air conditioners. How does your air conditioner maintain the temperature in the room that you're in? It needs to decide, does it need to turn on the compressor? Does it need to turn on the heater? Chemical processes. Every single thing around you is made of chemicals. Some of those chemicals come from processing plants where they are in massive reaction chambers, and they need to and the algorithms that exist on the chemical plant need to decide, should I increase the temperature? Should I add more catalyst? Should I decrease the amount of reactants? Financial markets, that's a pretty interesting one. If you've talked to quants, you might see them talking about stochastic optimal control theory, and that's sort of a whole thing of its own. And maybe you want to control the market to actually make some money. You want to understand the dynamics of how the market changes and what do you actually need to input. So, for example, how much to sell or how much to buy to actually get what you want. And physiological processes. The control theory isn't limited to engineered processes or stuff that's generally done with numbers, but also I have friends in the US, they've got some super interesting physiological, biological control sort of modeling. So neuromechanical modeling of how our muscles move, or how your body maintains heat, how your body maintains pressure and stuff like that. So we have all of these systems that need to be controlled. How does one actually go around and control them? Right. And that's a sort of big question mark. And the first sort of principle that you start looking at is that the real world is not a random system, right? You don't just give it random inputs and give random outputs back. The real world is governed by rules. These rules are physics, the physics of the actual system, or the emergent rules that show up in some sort of social or biological system, right? And so if our systems are governed by physics, well, physics is governed by this thing called differential equations. A differential equation is essentially an equation that relates some variable with respect to with its change. So for example, here I have a very general form of what's called an ordinary differential equation. It's saying that x changes, so x dot, the change in x with respect to time, changes with respect to some very general function of x itself, so of the state. Right. So for example, say you've got a system of, say, population and prey, right? Maybe you've got rabbits and you've got, I don't know, what hunts rabbits? Cats? I have no idea. But whatever it is, foxes, that's all. So say you've got a system of rabbits and foxes, and the population of rabbits and foxes forms something called a state, right? So imagine a vector, right? Just an array of two numbers, and that forms what we call a state of the system. And how does the population change over time? Well, you leave rabbits to themselves, you know what happens. And if you leave foxes and let them have their go at rabbits, you know what happens there too. So that you could define a dynamical system, a differential equation that describes how the system changes. So rabbits, the more rabbits there are, the faster that changes, and the more rabbits there are, the population of foxes also increases, for example. Yeah. So these systems, all of the systems that are around us, basically end up being differential equations, which are essentially describing physics. The systems that we want to control specifically are dynamical systems with some sort of input. So not only do they change by the physics that governs them. So for example, if I have a robot, not only is the physics of the joints and the rigid bodies together, the only one part, but there's also the input that we give them. So, for example, the motor voltages that we give them, or basically any sort of actuation that we have, hydraulic actuation, that sort of ends up being some sort of input. So we have a very general framework here now to describe any sort of system, X, with some state X, changed, and you've got some sort of dynamics or any sort of physics being described by this function f. Yeah. And this f may or may not take an input. If it takes an input, we can do control theory on it. Control theory's job, basically the entire field, is if you've got this some sort of system here, if this particular format, how do you pick u, and how do you pick u such that you can minimize some sort of error or move essentially to move the system that you want in a particular way that you want it to move, right? And a lot of the time what we do is we actually do something called feedback control. So not only do we need to choose u such that it minimizes this system or minimizes, not only does it need to move the way we want it to move, but usually we won't just think up how we want to change u on its own. We'll measure where the state is, right? And then we'll find where we actually want it to be, find an error, and then we'll make our input be some function of error. Does that make sense? Cool. So let's start off with an extremely simple example, the PID controller. Now this is the absolute most basic thing you can get, essentially. There's high schoolers that know this stuff. And there's more interesting ways to analyze this in, say, a third or fourth year course. But that's not what we're going through. And I'm going to introduce a toy model. That's something we use a lot in control theory. We have extremely interesting and complex systems like robots. But when we want to talk about control algorithms, we want to deal with simpler systems, right? Systems that sort of show the same properties that are more interesting in complex systems do, but without the actual complexity and without the difficulty of implementation. So the absolute most basic system that control theorists use for something that's vaguely interesting is what we call kart pole. And if you've done reinforcement learning or some other type of machine learning before, you might have actually come across this. So this is probably the most common example in OpenAI gym. The OpenAI's reinforcement learning sort of gym environment. And let's just describe it. It's basically just a pendulum. So you've got a pendulum here, so it's some sort of mass connected to a rod. And the special thing about this pendulum is that it's connected to a cart. And this cart is free to move, right? So it moves on some sort of rail or something. And what's interesting is that the system is nonlinear, right? So it's got, the dynamics of the system are extremely nonlinear and complex. But it doesn't have so many degrees of freedom that it becomes complicated. It shows the nonlinear behavior we want to control and think about. And it's quite simple to construct in real life. And it's quite easy to see visually. Like we have, if you look at a simulation of this, you have actually a pretty good idea of what's going to happen just based on our day-to-day circumstances. So how does the system move? Well, it has some sort of physics, and these are the equations of motion. They are not very pretty equations of motion. You've got extremely nonlinear terms, so you've got squares, you've got trigonometric terms, you've got multiple degrees of freedom. So for example, you've got, not only do you have a change in the position of the cart, but you also have a change in the position of the pendulum. And so this essentially ends up being a pretty archetypal system that we play around with. And being quite honest, dealing with nonlinear, highly complex and interesting motion systems is hard, right? It's sort of something we didn't really figure out until like 100 years ago or so. And that doesn't sound like a long time ago, but control theory is pretty old. So what we're going to do right now is we're going to show what control theory might look like just by looking at a particular controller for a simplified, or at least a simplified scenario where you might want to control this. So for example, maybe you've got the pendulum and you have the pendulum facing upwards, right? And what happens if you leave it upwards? It's going to fall, right? It's an unstable equilibrium. If you get it perfectly balanced, it's still going to fall. I mean, it might not, it does like some enough friction, but obviously that's not something we care about as engineers. So, yeah, so we want to control it at its unstable equilibrium point. And if it wasn't, if we didn't specify that, right, it's actually quite hard to do this. To actually get the system to move up like this, in a nonlinear pendulum, you'd actually need to like swing it around like this. I'm not sure if, is the camera on?
Yeah.
Cool. Yeah, so you'd actually need to swing your cart around and do something like this. And that's actually quite a hard motion to plan, mathematically speaking. Like, I don't think there's any analytical solutions to begin with. So, you know, it's actually quite hard to solve this, but the fact that you can deal with it in a particularly small region of interest is actually, it makes the problem quite easy. So, and we actually have some sort of intuition for this. So, if you look at this, if it starts falling this way, you sort of nudge it the other way, right? You've probably done this before. If you play tennis or something, you've tried to balance your racket around. You're playing around with an inverted pendulum on a card. So we sort of have some intuition, right? And some of that intuition is that if it goes away from, say maybe if it starts falling this way, right? Starts falling this way, you sort of push the card that way, right? So one simple controller that we could come up with is a proportionality controller, right? Depending on how far away it's fallen, you just increase the speed or the force on that side until it starts balancing out, right? There's other issues. What happens if it starts falling too much, right? Maybe it falls too much while you've done a proportionality term, and it was falling this way, you pushed it that way, but now it starts falling even further that way, right? So there's ways of dealing with that. What about you have an extra term, and you started having a force that's not only proportional to the error that you have, so how far away it is from the actual equilibrium, but also how the error changes, right? And you keep adding this you keep thinking in this way, and you actually come up with something called a PID controller. Yeah. It looks a bit complicated, but it's not, I promise you. So this is your input. Your input is this error, so the error at time t, multiplied by some value kp, so we're going to call this our proportionality gain, right? And then we have a derivative term. So here we have the change in the error, and so this is basically going to account for if our pendulum is falling too far the other way. And then you have integral term, and it's actually not applicable for this particular system, but sometimes you have a system where the force that you're trying to put in has a balancing counter force, right? And say, for example, actually if you're lifting something up, like this mug over here, you want to put it over here, and you put some force up, and at some point it's going to come close enough that the force that you have, the proportional force, is not enough to actually lift it high up enough, and the gravity is you actually need to compensate for that. So this extra term here just integrates up the error, and so if the error stays up a bit too low, if there's a steady state error, it just integrates up, so there's zero steady state error. So at the end of time, there's basically zero. Cool. So the result of this control is actually quite nice. It actually is quite easily able to maintain this control even in the face of disturbances. So if you give it random forces left and right, it'll be a bit robust. You can maintain it in that sort of situation. But there's a few problems here. So what happens if it falls too much, right? If the pendulum falls too much in this direction? Well, any sort of assumptions that you made about how this system is going to behave sort of die, right? So if there's a small amount of error in this direction, and you push in this direction, with small angles here, it would actually balance out, right? If it's almost 90 degrees, you pushing it left is actually not going to do much. It's just going to push it further left. So how do we deal with that? And the other thing is this actually doesn't really give us a lot of control. This system can't really work to maintain like arbitrary angles, right? Or You can't, for example, start at the bottom and go to the top. So how do we do extremely interesting things like this? So this is a triple pendulum. This is 3 pendulums stacked on top of each other, and the only control you have is the card. And that's an actual controller that someone worked on, and I think that's the even more interesting thing it can do. But how do you do interesting things like that? And there's actually, in the last 100 years or so, we've come up with an entire field called modern control theory. Specifically, there's a lot of interesting work on optimal control theory and numerical optimal control theory. And I'm just going to gloss over them for now, and we'll sort of talk about them in a second. But today I'm just going to introduce one particular type of controller. It's called a model predictive controller. Now this actually, this has an interesting story because, well, most of control theory happens in academia, right? So there's like researchers in the back of some basement, and they like do some maths, and they come up with like theoretical bounds and proof for some controller being stable. This is actually an interesting case because this is something that came out of industry, specifically the chemical engineering industry. So some guys that were getting paid like 10 times more than the actual academics, they came up with this controller, and it actually, it worked really well, but academics didn't touch it for like, I don't know, 10 years or something because they couldn't figure out how to prove theoretical guarantees for it and stuff. But it's an interesting controller and an interesting idea. And I'm just going to show you this diagram of what the idea is, and we'll get back to the diagram in a second. But I just want to show you there's going to be some sort of input reference. Oh yeah, by the way, this is a block diagram. We use this all the time just to express the flow of information, the flow of how everything works in our system. So you've got some sort of reference that you want to maintain. So maybe you want to maintain it at a particular temperature, you want to maintain a particular yield in your chemical reactor or something. And it's going to have two things to be concerned about. There's the process itself, so there's the process. So in this case, the process here means whatever system you want to control. It's a chemical engineering term, so it's from chemical engineering, so we call it process instead of system. Or so this could be a robot, this could be a car, this could be a jet, a rocket, whatever. And then you've got the actual controller, and the controller has been split up into 2 parts. It's got an optimizer, and it's got a prediction model, and it's got some sort of inputs too. These extra inputs called the cost function and the constraints. We'll get to that in a second. So how do we come up with this? Well, we can start off with our goal, right? So our goal right now is to deal with a highly complex and highly nonlinear system and do it with feedback, right? To be able to take advantage of measurements, so we actually can deal with stuff live. And we want to take advantage of the knowledge that we have of its physics, right? It's really hard to control a triple pendulum, but it takes like 20 minutes for me to derive the actual nonlinear equations of motion that actually describe its behavior, right? So we want to take advantage of this knowledge of physics and our ability to simulate this system, and we want to do it. We want to make it do extremely interesting motions, so highly dynamic for a robot, highly agile, etc. Now, our weapon of choice in this particular controller is something called optimization theory, right? And many of you guys would have studied optimization theory, even if it's very basic kind. In high school, you would have done the derivative equals 0. In university, maybe you've done something like Newton's method of optimization. Maybe you've done gradient descent if you're a machine learning person. But there's a whole field of optimization, and it sort of deals with this system. How do we minimize some X or X objective, and how do we do it with respect to some constraints or how the system behaves, etc. So our system, so incorporating this massive weapon into our system, we're going to try and minimize some sort of cost or maximize some sort of objective, and we're going to have some constraints that the physics of the system can't change, or in other words, whatever controller that we come up with, it has to follow the physics of our system. Now that's where robotics and control theory differs from game developers. We actually have physics to listen to, and game developers just sort of have to look right. And then you might also have some other constraints about what your control should look like. Now this might be because you know that's a legged robot, and you sort of vaguely know what it should walk like, right? It should have legs, and it should like step like this, right? So you might have other constraints. So I'm going to teach you guys a trick. It's called walk the dog, right? And we're going to show you how we can get a controller to get a walking robot dog, right? Something like a Spot or an Animal, if you guys are familiar with legged robots. And we're going to show you some optimal control theory. And yeah, so the optimal control theory is going to be a field, the field of control that deals with controls such that the controller minimizes some sort of cost function, right? And there's actually an absolutely broad, field. There's like many different ways of approaching this. If anyone has done a course like Math3404, they would have also even done a little bit of optimal control there. Now I'm going to show you a very scary looking equation. This is the cost function. Now, let me just show you here. So this is what we call the overall cost of the system, right? And this is your cost at the boundaries. So essentially, what is the cost? And we're going to define the cost ourselves later in a second. So what is the cost that we want to minimize? And this cost has two terms. This has the boundary terms, so the cost of starting at a particular location and finishing at a final location, and also the running cost. So as your system takes its path, so as your robot takes its trajectory, or as your car moves in this particular lane, etc. Sorry. What sort of you sort of want to sum it over, so you want to integrate over it. So from the starting time to the ending time, you want to add over all the running costs. And so this is the overall cost functional. And the goal of optimal control theory is to minimize this cost functional. In fact, you want to say it wants to choose your input, such that it minimizes this cost function, and we call that the optimal controller. Or if you guys are, if you're from reinforcement learning, it'd be called the optimal policy. But yeah, so this is optimal control theory, and we want to figure out how we can use these tools of optimization and these tools of optimal control theory in order to control something like a legged robot. Yeah. Now, what is a legged robot? You guys might think it may be like a robot with some sort of torso and it's got legs with all of these extra bits. As a control theorist, I strongly disagree. A legged robot is just a block of mass with 4 possible places where it can put forces. Right. So this is a quadruped. We do not care about joints. We do not care about anything else. For the purpose of modeling, we're going to say that it's literally just a solid, rigid mass, and legs are massless objects that are able to provide forces in the upwards direction, and they have some sort of constraints on how they can provide forces. Right. So this is our system. We want to solve it with optimal control theory. How do we do it? First step, we want to define a cost. Right. Now, what's the useful cost? Well, there's a lot of different costs we can choose. I'm going to choose something that's nice for us. So you want your legged robot, and you want to show it to your friends, right? And the first step to that is actually walking your dog to your friends. What you don't want is your dog running out of energy. So how about we minimize the torque, right? Torque is vaguely proportional to the current, which is vaguely proportional to the energy that you have in your system, in your battery. So if you minimize the torque, you minimize energy consumption, right? So that's our first cost. And now what we're going to do is we're going to introduce a bunch of constraints to the system. So we've won the first part of optimization problem. We want to minimize this torque term or this energy term. And then the rest of the optimization problem is the actual hard part, right? How do you define an optimization problem? If you came to the Tuesday talk, you sort of know the constraints are the hard bit. There's entire books not on how do you solve optimization problems, but how do you phrase something as a useful optimization problem, right? And that's not specific to robotics. That's pretty much every field that uses optimization regularly. The most important part is having a good definition of your optimization problem. So we start off with a few things. So first of all, we want the robot to be able to walk. So the robot's physics need to be followed, right? The robot has some physics, the dynamics, that we talked about before. we need to enforce that whatever input trajectory that it comes up with, it needs to respect the physics of the robot. It needs to make sure that the robot doesn't, it's not inputting infinite torques. It doesn't have any sort of it doesn't phase through a wall or something. So that's the first most important constraint. Then we want the robot to go from some particular point to another point. And so that's two more constraints, right? So it starts off here and here, and that's an extra constraint that you place on the robot. And the next is, it's a legged robot, right? The legs can't go below the ground, right? At best, they can go on the ground. And they can only push down on it, right? When was the last time you, stepped on something and you got pulled down with? Well, probably the last time you stepped on like a chewing gum or something, but we're assuming the robot doesn't step on chewing gums, so the leg can only push down on it, yeah? And this one's not actually necessary. You don't need the leg to not slip, but when was the last time that you tried walking while slipping? Maybe when you were ice skating, but that's not what we're trying to get the robot to do. We're going to enforce another constraint. The leg can't slip on the ground. And we're going to tell you how we can define these constraints below. So we have this. Now this is a bit daunting looking, but it's basically the same thing we just described, but in slightly more macro terms, right? So you have this cost function. So this tau is your torque, and you want to minimize the torque squared. And you want to sum this up from 0 to the final time. And you want to choose x, your robot state, and your input, u, such that it minimizes the function. Yeah? The effect of that will be that you'll be minimizing the amount of energy spent for your robot. Now the next thing is we actually need our computer is sort of discrete. We don't have continuous computers, at least not any good ones. And so we actually sort of need to discretize the problem, right? And there's a lot of ways to discretize the problem, but essentially what we're referring to are integration algorithms. Yeah, you guys might have done this in some of your math courses. The easiest way to do this is Euler integration, right? So if you have, say, some sort of system, you can essentially get a discretized version, the next state of the system, by taking the derivative and assuming that your system changes linearly, and just multiplying it by some short amount of time, dt. And so your next state, so xt plus 1, is xt put into your f and multiplied by your dt, so a small amount of time. Yeah. Now, remember your high school physics. There is something called static friction. And if your static friction essentially is some sort of force that opposes any sort of transverse motion on this ground. And they're essentially saying that if you've got some sort of normal force, there is static friction coefficient such that if you have a tangential force, so for example, if you have force downwards, Fn, and you multiply it by some coefficient mu, this is called the static friction coefficient, then this is going to result in some sort of bound for how strong your side-to-side forces can be. And so this statement is saying is as long as the side-to-side forces is lower than your normal force, your downwards force multiplied by the friction coefficient, this system is fine. And this has the effect of making sure your foot doesn't slip. Another constraint that you can place is the foot. So your foot has to be touching the ground, right? In the most simplest case, you can say that the entire world is some sort of ground, like it's like a flat ground. Obviously, that's not realistic. In an actual robot, what you would see is that the robot is able to, it has some vision, so it has either LiDAR or depth cameras or a camera with a neural network that estimates depth. So it has some 3D information about the world around it. And it has some sort of world map. And what we're going to say is that as long as the foot is touching the ground, the location of the force should be, location of the foot should be this. Yeah. And lastly, it's pushing down. So the force normal, so the normal force should be downwards, and therefore it should be less than 0. Now we've written this as a formal optimization problem, right? Now, we actually need to sort of think about this. So we need to express this to an actual optimization solver, and there's many on the market. So there's nonlinear programming solvers, there's quadratic programming solvers, and we sort of need to implement this in code. Usually it'd be C++, something that's pretty fast, something that's low latency, and the actual magic. We'll talk about where the actual magic of model predictive control comes from, but this is actually able to make some pretty interesting motions. So this is basically an entire field of research, and it's able to make some pretty interesting motions. So for example, here's a robot called Animal, or Animal, I'm not sure exactly. Animal makes more sense to me, but so you've got your rigid body mass, and you've got your force inputs here, and you've got these things called friction cones, and they're essentially saying that if the friction, as long as the friction on the left-right direction doesn't go above your max static friction, this is fine, and that basically results in something called a friction cone. So as long as your forces are within the friction cone, your foot isn't slipping. Yeah. There's extra stuff that I haven't mentioned. There's a lot of nuance in how you can specify this optimization problem. So realistically, what you would want to do is also you want to specify your gait pattern. So I told you here, here, that while the foot is touching the ground, it should be, while the foot is touching the ground, it should be on the ground, right? But it doesn't specify when exactly the foot should be touching the ground and how exactly are the contact forces, how do the contact forces work, etc. You sort of need to define a gait pattern of when this foot needs to be on the ground, when it doesn't. And there's fancy ways of sort of trying to get around that, but it sort of makes the it makes the walking a bit harder if you don't formally specify what the walking should look like. If you know anything about animals, you might know they have different gaits. There's like trots and like bounding gaits and stuff. Those are pretty common patterns. You would just specify. They have like particular timing constraints, and you can specify those during optimization solver. Lastly, you know that the last thing is you know that your system is some sort of continuous function, right? So your position doesn't change randomly. And it doesn't change, probably shouldn't change in erratic ways. So other constraint that you can put is that maybe something like the position of this robot shouldn't just randomly move around. You shouldn't try and optimize every single point within your discretized trajectory. Maybe you should be optimizing for a smaller space. So for example, instead of saying that you're trying to optimize for like 100 variables for 100 periods of time, it's like 100 moments of time within a second, that's a lot of optimization variables to solve for. Instead, maybe say your trajectory, your motion is given by some polynomial function or a Bezier curve or something like that. And instead of trying to solve for every single one of those points, you're trying to solve for the 2 or 3 different parameters that define that spline. Yeah. Now, we've described how you can make an optimization problem with all the constraints to get robot dog walking, right? Now, where is the magic? Why do we call this model predictive control, right? Now, if you go back to this, you remember that not only do you have to have an optimizer and a predictive model, it needs to feed back from the process back into your system, right? So an optimization problem on its own is really cool, and in theory it could make an interesting problem, and there is a whole field around just making interesting trajectories, and it's called trajectory optimization. But to actually make this work in a real robot, usually what you need to do is you need to do feedback, right? So if every single mistake that you have, every single inaccuracy in modeling the dynamics of your robot, so if your weight is slightly wrong, or if your motors don't put out as much force as you expect them to, that's going to cause issues in your model. And you need some sort of feedback to understand where your location is, and you need to feedback. And so the solution to that, and it's not really obvious in this framework until I tell you, is that you just solve this problem really, really fast, again and again and again, right? So if you're not accurate in your system and you can't predict, for example, what inputs you need to have for the next 10 seconds to walk from here to there, maybe you have an accurate enough model that you can predict it in the next 20 milliseconds or maybe a whole second, right? So if you run this process again and again with changing initial conditions, you'll essentially have a pretty good idea of you have a pretty good idea of how you need to change at any particular moment in time, and have you'll have feedback built into the system, even though it's not actually feedback that's built into the algorithm. So if you remember your PID controller, the PID controller's output was essentially directly based on the error term. The error term was from a measurement, and there was direct feedback there. Now this time we don't have that. It's not based on any type of error term. It just knows our current location, our goal location, and tries to optimize that. We get the feedback by trying to run this problem again and again with different initial conditions. And this is exactly what Atlas does. So Atlas actually has two stages. Atlas has what you call a centroidal dynamics-based trajectory optimization stage. In this particular stage, it'll start off by having centroidal dynamics, so basically approximate the entire robot as one rigid body with a few forces that it can have, so exactly what we did with our robot. That's the first step, and it uses that to come up with interesting motion. So for example, if it wants to move from this location to that location and needs to jump between obstacles, it doesn't need to consider all of its particular joints. It doesn't need to consider each of its individual joints. All it needs to consider is what forces do I need to put. So for example, I need to jump from here to here. It doesn't matter what my fingers are doing. It only matters that we have enough force here to get there, right? So you you have a first stage which simplifies the system into centroidal dynamics, so approximate as a one rigid body with forces. And then there's a second phase, and that's the model predictive controller phase. So in the first stage, you would have a low-dimensional model solving a low fidelity model solving a extremely complex problem. And the second stage is a model predictive controller, and this one uses actual feedback, not just the next 10 seconds, but use the current information you have and solve for the next 100 milliseconds, something like that, and use that to actually follow the trajectory that the first step made. Yeah. So what do I need to do with my finger and my toes to actually impart the forces that my first step calculated? And that you can actually sort of see this, right? So we can see a lot of the behavior that we expect. I mentioned that in the real world you actually have some sort of perception system that tries to figure out where the actual ground is, and you use that as constraints. So if you can see, it makes these polygons every time it wants to step on something, and that's your foot constraints. It also has a gate planner, so as you can see, it tries to plan out where its footsteps need to be, and then it tries to solve an optimization problem on how to get there. And you can also see this model predictive controller. So it only has a particular horizon, so it only looks ahead so many seconds, and it plans ahead that long, and then as it's going around, it sort of readjusts. So you'll see that as it sees new obstacles, or it sees that that its last motions were a bit off, it compensates for that. Yeah. And that's sort of my whole talk. I just wanted to introduce to you guys how such a complicated robot can do such interesting and dynamic motions, and I wanted to introduce control theory, and I think I did that all right. And thank you so much for coming. If you guys are really interested in this, there's some subjects you can take. So if you guys are mechatronics, electrical, or mechanical people, METR4201, 7203, and 4202 are the most relevant courses. They basically go over classical control theory, modern control theory, so more of the stuff that we talked about in the last half hour, and also METR4202, robotics, which is sort of a bit more on the system modeling and physics side. Very relevant to this course also is any sort of numerical optimization course. So numerical linear algebra and optimization theory, that's Frank Lewis's Math3204, very interesting course. And also, I forgot to list it here, but Math3404, optimal control theory and calculus of variations. So yeah, that's the most relevant course at UQ. If you can't do those courses, you don't have the electives or anything, I would go straight to one of these resources. The last one's a bit more on the physics side, so it deals with nonlinear dynamics and a lot on chaos theory, which is extremely relevant to our system. So if you remember, the triple pendulum that we tried to control is a chaotic system, and we're still controlling it, but it's sort of studying the behavior of the system sort of falls in the same league. We have the lectures on nonlinear systems by Slotine. Great lectures, and the absolute best text on this is Underactuated Robotics. It's an online textbook by Rusted Drake at MIT CSAIL, and it's a pretty great resource for anyone interested in this type of stuff. Thank you for coming. Does anyone have any questions?
If you go back to that last year, you said that some of it was the gift.
This one?
Yeah, you said that some of it was pre-planned and some of it was perceived. Which parts here are pre-planned?
So I don't remember exactly. So we don't have full details, and I don't remember exactly what's pre-planned and what's not. But I do know that in the first step, it's basically they have a bunch of stuff running offline. So they have the trajectory generation that happens offline, and they essentially come up with interesting motions. So for example, you want to jump over an obstacle, that's a particular behavior that you want, and you can do trajectory optimization beforehand and get a solution for that. And you can essentially put it into a library of motions you can do, right? So this particular robot, it'll have had stepping over an obstacle, it'll have jumping between platforms and also backflips and whatnot as pre-planned, optimized motions in a trajectory optimization step, and it'll sort of remix that on the fly. So it'll choose what motions would get it to the objective it wants to follow, and then it'll follow that live with model predictive control. I'm not sure exactly what's going on with the perception, because it seems to vaguely know where stuff is before it gets there. I would assume that it either builds an occupancy map, so like builds a map where stuff is in the first runs when it's going in the other direction. So as you can see, there's like when stuff is blue, it means it's not visible, but it's sort of there's sort of a plan for what's there. So maybe it's either pre-mapped, which I don't think it is. I think more likely the first run that it had, it mapped it itself and then came back and replanned it as it perceived it again. Anything else?
So it has like a map before it starts the trajectory to like localize itself?
So it can have, I'm pretty sure it doesn't start off with a map. So I think it would be told waypoints exactly where to go in like physical space, and it'll be able to tell how, so maybe it'll say from here go 10 meters that way, and it'll have to figure out how to do it. And so there's a sort of a whole obstacle course, and I think the first time that I ran the course, it maps the obstacles, and second time when it goes around the sort of slanted platform that came back around, it used the existing knowledge that it had of the environment from like a minute ago, and then pre-planned its motion beforehand, and then it just recalibrated the motions when it came back into view and could perceive it. Any last questions?
Have you had the chance to like work on any robots using this?
So I have done a bunch of stuff in simulation because I don't have legged robots yet. Yet at Cyro we do have a bunch of spots, and also at Emerson where I'm about to start my grad job in a month or so. We also have spots there, but spots sort of don't let you do that sort of stuff. But I've done a lot of this in simulation with trajectory optimization and model predictive control, but not with legged robots for sure. Oh, I have. There is a very interesting course. So if you do METR4203 now it's called, there is a very interesting nonlinear system. So it's basically a gyroscope coupled pendulum. So you saw the inverted pendulum. Now imagine you couldn't actually control the cart. In fact, the cart was actually a gyroscope, and you had to spin a gyroscope and then cause torques on the spinning flywheel to cause gyroscopic torques. left and right. Now that's probably the most interesting system that you can do nonlinear control at UQ. So if you're interested in that, take METR4203. And anything else? Cool. Thank you guys for coming. It was pretty fun talking. Even though I made this like 90% of these slides like 6 hours ago or something. Cool. And is Peter here yet?